Good morning, class. My name's Philip Grudier. I'm one of your fellow online students, and I'm here to talk to you about the paper regarding oxidation of hafnium carbide and hafnium carbide with additions of tantalum and praseodymium by Courtwright and Gang. In the introduction of this paper, they pretty clearly state that carbon-carbon composite materials are of interest for the application of engine turbines, engine turbine blades, because of their low density and high strength at the elevated temperatures that you would want to operate your engines at. The one factor that is preventing them from being used in these applications is the fact that they oxidize and lose a lot of their material properties, and so this paper seeks to examine the protective coatings that one could use to try to protect carbon-carbon composites in an engine environment. So given that you're looking at a high temperature application, you need metals that are going to withstand high temperatures. They're not going to melt at the elevated temperatures. This paper specifically stated that you'd want to start using these materials, or these carbon-carbon composites, once your engine got to about 1,800 degrees Celsius. And so the only refractory metals that would be able to withstand that temperature would be thorium, zirconium, hafnium, and beryllium. Of those, thorium is radioactive, so probably not a good option if you're trying to build an engine turbine. Zirconium was a good option. Beryllium was not a good option. It's potentially toxic. In my workplace, we do treat beryllium as toxic. There's a lot of environmental hazard related concerns with beryllium. So again, not a good option. And then hafnium is the other good option. So between zirconium and hafnium has a better diffusion barrier than zirconium, despite the relatively high oxygen mobility through hafnium. And so this paper decided to examine and probe what hafnium protective layers could look like. Additionally, due to thermodynamic concerns, you would want to use a carbide. I assume, though the paper does not specifically state this, I would assume that you wouldn't want to have just a metal because of the galvanic corrosion concerns. So they probe hafnium carbide protective solutions. In addition to hafnium carbide, they mixed hafnium carbide with 25% or 25 weight percent tantalum carbide and 10% praseodymium carbide, and the tantalum carbide was supposed to increase oxidation resistance because tantalum in the hafnium tantalum alloy does significantly increase your oxidation resistance because it produces a tenacious oxide layer, and then praseodymium reduces oxygen permeability in growing oxide layers in the praseodymium and hafnium alloy. So they wanted to see if these trends were true in the carbide combinations. For specimen production, they used a hot press to try to compact their hafnium carbide and then the hafnium carbide tantalum carbide combination in the hafnium carbide praseodymium carbide system. The results of their pressing are shown in Table 1, where you can see what the pressing conditions were, what the resultant densities were. Then they moved on to explain their experimental procedure. Now, this was one of the areas of the paper where I did not appreciate their procedure. At the common temperatures currently used for turbine materials from 1,200 degrees Celsius to 1,530 degrees Celsius, they tested their carbide systems in using thermogravimetric analysis, which is something that we're familiar with, due to our textbook and the early days of our class, where we examined what that analysis looks like. And then for higher temperatures, from 1,800 degrees Celsius to 2,200 degrees Celsius, they used a later heating apparatus. Now, the difference between these two methods are, with thermogravimetric analysis, you lower your sample into a heated zone, and then you're measuring the mass gain associated with your oxide growth. In this paper, they clearly stated that as they were doing this analysis, in the data analysis step, they assumed that the oxide growth was 100% dense, which, as we will see, that is not a good assumption. These oxides that were formed were rather porous. And then with the laser heating apparatus, they would isothermally heat a sample, oxidize it, and then metallurgically examine the specimen afterwards to measure oxide thickness. So they're using two different methods to develop the oxides. They're using two different methods to analyze oxide growth. And so I think this is one of the weaknesses of the paper, is that as we'll see later on, there's going to be this bifurcation in oxide kinetics, in oxide growth kinetics. At the lower temperatures, they behave one set of rules, and at higher temperatures, they behave another set of rules. And I think that a critique of this paper is, well, you've used two different systems to analyze your oxide growth and your oxide growth kinetics. And so when you get different results, it's not 100% comparable. It would have been preferable to use one system across all temperatures. And the paper didn't specify why they couldn't use one process across all temperatures. So I would like to either see an explanation of why one system couldn't be used across all temperatures, or why these two systems are comparable in your data analysis. Then they moved into the results section of the paper. They did see parabolic growth of their oxides, and so the parabolic rate constant that we're familiar with kept popping up in the paper. Then they went and discussed each of the three systems that they wanted to probe. So first was just hafnium carbide. And again, as I alluded to earlier, there was a bifurcation in what the kinetic growth constants looked like. Below 1,800 degrees Celsius, they behaved one set of laws that you can see in the PowerPoint that I attach, and then at the lower range they behaved one way, and then above 1,800 degrees Celsius they behaved another way. So yes, the rates were different. At low temperatures, the rate was higher, and then at high temperatures, the oxide growth rate was lower. And then they examine what the metallurgy of these oxides look like. They did confirm that hafnium oxide was formed. They verified this by XRD, and it was at ambient temperatures. It was monoclinic hafnium oxide. The hafnium oxide phase diagram suggests that above 17,000 degrees, or 1,700 degrees Celsius, the oxide should grow as tetragonal. And so the tetragonal to monoclinic transformation has an associated 12.7% volume change associated with it. So they compared the cracking patterns between samples above and below transformation temperatures, and they did notice that the cracking patterns were similar, and so this does not appear to be the major reason for cracking patterns, and they will discuss the reason for the cracking patterns later on, the cracking patterns and the porosity formed later on. In the hafnium carbide, tantalum carbide system, again, another bifurcated oxidation kinetic regime, where at the low regime, below 1,800 degrees Celsius, you had high oxidation kinetics, you had high rate of oxidation of oxide growth, and then at the lower, or rather at the high end, you had lower rate of growth. So the hafnium carbide and tantalum carbide oxidation kinetics above 1,800 degrees Celsius were comparable to those previously reported for the hafnium-tantalum alloy. You did have tenacious crack-resistant oxide that forms on the hafnium-tantalum alloy, whereas the oxide that formed on the carbide was porous and prone to cracking. In the metallic system, you have the internal oxidation of hafnium resulting in a lamellar structure where the hafnium oxide platelets help, they grow, there's internal growth, and they act to anchor the oxide to the alloy. No such mechanism existed for the mixed carbide. Thus, the oxide that formed on the carbide was, additionally, the oxide that formed on the carbide was weakened by the presence of pores. In the hafnium carbide, praseodymium carbide alloy system, in the hafnium carbide, praseodymium carbide system, the material displayed runaway oxidation, and thus no rate kinetics could be obtained. The hafnium carbide, praseodymium carbide generated excessive heat that made temperature control of the laser impossible, and the above oxide layer periodically disintegrated into a fine dust, and XRD indicated the presence of both monoclinic hafnium oxide and cubic hafnium oxide in roughly equal amounts. Since this oxide was not protective and disintegrated, they did not do very much analysis in the future of the hafnium carbide, praseodymium carbide system. This does not seem to be an effective way of protecting a carbon-carbon composite at high heats. Additionally, they attempted and succeeded in thermally cycling their parts. They did 5 thermal cycles between 2,000 degrees Celsius and 500 degrees Celsius. I've attached the 2 pictures of what happens in the hafnium carbide system and the hafnium carbide plus tantalum carbide system. Hafnium carbide did not see any noticeable impact by thermal cycling, whereas the hafnium carbide and tantalum carbide were clearly damaged by the thermal cycling. Additionally, the hafnium carbide and tantalum carbide system saw approximately double the growth kinetics of the isothermal system. Thus, in reality, it looks like the hafnium carbide and tantalum carbide is not a very good protection system, since if you're using it in an engine turbine, you're going to be turning on and off your engine. Your engine turbine system is going to see thermal cycling, and so if you're going to see the degree of damage and the increased rate kinetics, it looks like that protection scheme is not going to fit the desired outcome. The discussion of the paper discussed the similarities and the differences between both of the carbides and the alloys, and so some similarities with the metallic alloys. All of the protective oxides grown on the carbides displayed parabolic growth kinetics, and there was evidence of internal oxidation for tantalum carbide and for praseodymium carbide. Some major differences: the fact that in your carbide system you have carbon, the oxidation of carbide creates carbon monoxide as a byproduct, and carbon monoxide is virtually incapable of dissoluting into any oxide layer, and as such, as you're oxidizing, you get a buildup of carbon monoxide, and it seeks to escape. And so that's why a lot of the porosity was seen. They believe that the carbon monoxide is outgassing through the oxide and is creating pores as it escapes. This has the advantage of allowing the carbon monoxide to escape, so you're not getting catastrophic failure of your oxide. But then the downside is you have through pores and you have porosity in your oxide, and this is going to allow oxygen. This is going to allow fast paths for oxygen to diffuse through. So that's not helping the kinetic side of your equation. In addition, particularly in the praseodymium carbide system, and also additionally in the tantalum carbide system, the carbon monoxide gas formed below the oxide layer was able to lift and disrupt some oxide layers, forming pretty gnarly oxides. Moving on to the growth kinetics for the hafnium carbide and the tantalum carbide systems, the fact that they were discontinuous based on temperature dependence suggests that there's a change in the rate controlling mechanism for oxidation. The paper believes that above 1,800 degrees Celsius, that solid state diffusion is controlling the kinetics, since the temperature dependence of the oxide growth rate is close to the oxide growth rate observed on metallic hafnium and the hafnium carbide, or the hafnium tantalum alloy system. So above 1,800 degrees, the solid state diffusion and your kinetics look similar to your alloy system, but below 1,800 degrees Celsius, the oxide growth is much faster, and they believe that that is because the oxide growth is controlled by oxygen, carbon monoxide, and carbon dioxide gaseous transport through these interconnected pores, allowing oxygen fast access to the oxidation front, since there's internal oxidation. And they also stipulate that they believe that at high temperatures, the oxide sinters a little bit, and this provides less effective volume for gas diffusion to and from the surface. And so that's one reason that you see the slowdown in oxidation kinetics and the similarity between the carbide system and the alloy system above 1,800 degrees Celsius is, again, this sintering effect. The paper then goes on to discuss this diffusion through the pores. Again, below 1,800 degrees Celsius, the rate constants are substantially higher than expected for lattice diffusion, and so this suggests that there's some fast transport of oxygen through the oxide, and so pores would be an avenue for that, and so gaseous diffusion through a continuous pore network seems like a great candidate for why there's this higher than expected lattice diffusion, well, higher than expected diffusion in comparison to a lattice. So they also state that the carbon monoxide, the oxygen, and the carbon dioxide reactions are going to establish an equilibrium throughout the scale, and so at the carbide interface, you have carbon monoxide being evolved, carbon dioxide, and nitrogen. And then in the outer region of the scale, you have oxygen, carbon dioxide, and nitrogen. So in between those two regions, you're going to have some flame front that exists where your carbon dioxide is reacting with oxygen to create carbon dioxide. And so that's creating a concentration gradient. So your carbon monoxide is going to be diffusing out towards your gas through your oxide, and then oxygen is going to be diffusing inwards towards that flame front, and then the reaction is occurring at that flame front. The paper does some analysis based on Stefan Maxwell equations, and to try to calculate concentration profiles. In the PowerPoint presentation I've attached, you will see what they believe those concentration profiles look like, and again, it shows the same thing, that at your carbide interface, you're having carbon monoxide evolved, you have oxygen diffusing in and then reacting at a flame front. They also went on to iteratively solve fixed diffusion equation and the thermodynamic equilibrium equations, and they used these to predict that you would get a parabolic rate constant. So that's good when your model is matching your data. It's a good thing. And then this parabolic rate constants were calculated for a family of pore radii at 1,400 degrees Celsius, and this model successfully predicted the value of the rate constant that was consistent with the experimental findings. Finally, they determined that temperature found temperature to have little effect on the calculated curves of the parabolic rate constant with pore radius, but that pore density and pore radius had large effects on your parabolic rate constant, and that's to be expected, particularly at the 1,400 degree regime. And this is because they saw this in their experiments, that at lower temperatures it seemed like gas diffusion was finding some fast path through pores, and so as your pore density increases and as pore radius increases, you would expect your parabolic rate constant to increase as you get more oxygen diffusion to your oxide. More oxygen diffusion that would allow for oxidation, internal oxidation to occur. Finally, the paper had a summary. Again, the summary is that they saw parabolic growth on hafnium carbide and with the addition of tantalum carbide. Below 1,600 degrees Celsius, kinetics dominated by gaseous diffusion across the oxide layer, and this was via pores. And then they created a model that described this behavior, and they discussed how their model matched up with their findings. Above 1,800 degrees Celsius, kinetics were controlled by diffusion of oxygen through the oxide layer. And of course, this diffusion was augmented by porosity, but the diffusion through the pores was not as critical or as large as below 1,800 degrees Celsius. The oxidation of hafnium carbide produces carbon monoxide gas, and since that cannot diffuse through the lattice, this causes the formation of pores as carbon monoxide is trying to escape from the surface, from the oxidation front. This weakens the oxide, and it increases your cracking in your oxide. To improve the performance of protective oxides that are based on hafnium carbide systems, at low temperatures, it looks like you'd want to search for additions that enhance the sinterability of your growing oxide layer. And then oxide cracking and spallation was prevalent through all of their experiments, and that was found to be a problem faced by all their hafnium carbide based systems, and that was, again, due to thermal stresses. Finally, the addition of tantalum carbide and praseodymium carbide to hafnium carbide does not improve oxidation resistance and so those do not look like good additions to hafnium carbide if you were looking to put those on carbon composite turbines. Thank you very much for listening. I want to encourage you to ask me questions, to make any comments. Again, I think an interesting point of discussion would be the fact that they used two different experimental methods at two different temperature regimes, and then there was difference at those two temperature regimes in their oxidation kinetics. So if you have thoughts, I would love to hear them. I'm sure the class would love to hear them. So I look forward to future and further discussion on this paper. Thank you very much.